Up to this point, we've talked about limits and how functions can approach a certain value as x approaches another value. But we really haven't got calculus part of it, that calculation of just what does it mean. And while limits are nice, and it is something that we need, we absolutely must have the concept of the limit, otherwise all calculus falls apart. But while that's interesting, provides background knowledge, in practice, it's not all that useful. One of its applications, however, is, and that's derivative. And so we're looking at tangent lines and derivatives and how the two uh, define one another. So let's go ahead and start with just looking at some specific function. And it's a specific function, and yet not. I'm not really defining the function. I'm just going to put a curve here. Okay, so we've got a curve just going off on doing its own thing. And we've got 2 points on that curve. We've got a point 1 here, and we've got some other point 2 here. And without calculus, we know that we can go ahead and draw a line between these 2 points, at least a semi-straight line, and we can find the slope of that line. And we know that the slope of g of x, in this case, is equal to y2, or the y-coordinate of the second point, minus y1 over x2, or the x-coordinate of the second point, minus x1. And that's all fine and good. And this other one we'll call f of x. And so we know that if we have some function f, then we can draw some line g between any 2 points on f, and we have a slope. We can find a slope there. Now, if that line cuts in 2 spots, or more than 2 spots, that is known as a secant line. And secant means to cut. Also, we really could say something about it. That's kind of the average slope of that line between those 2 points. But what we'd really like to know is, what is the slope of f at any point? So if we were to draw an infinite number of these pairs, could we then choose a pair and say, well, that's the slope of f at between those 2 points? Okay, well, let's go ahead and just kind of define what these points are a little better. And if we let the distance between these 2 points be delta x, let's call this one x and this x plus delta x, so that if we were to find the f values, or the function values, the function value of point 1 would be f of x, the function value of point 2 would be f of x plus delta x. You'll notice in place of x, I have x plus delta x, and we'll need that idea later. So now, what I'd really like to do, though, is rather than keep drawing 2 points, 2 points, 2 points, 2 points, is it possible for me, knowing what we know about limits, to squeeze the distance between these 2 points so small, 2 will start writing down so small that we can't discern between one or the other? And so, again, we bring back this idea of the limit. And if we want to do that, to squeeze it down so that the distance between these 2 points is so small we can't tell the difference, then we would have to take the limit as delta x goes to 0. Now, as delta x goes to 0, the distance between our x values for our points is going to decrease. But we've also learned through the delta epsilon definition limit that we'll experience a decrease in the distance between our function values as well. In fact, if we're good enough, we can squeeze it down, and so we could find the effective slope at any given point. 1 point. That's it. So let's go ahead and squeeze delta x down to 0 and see what happens. Okay, well, if we did that, then putting in what we know, we would have y2, which in this case was f of x plus delta x minus y1, which is f of x, divided by x2, x plus delta x, minus x1, which was just x. And now we clean this up a little bit with algebra. If you notice this here, we have a negative x and a positive x. We can cancel those out because anything minus itself is 0. And so we have the limit as delta x approaches 0 of f of x plus delta x minus f of x all over delta x. Now remember, we started this with a specific purpose in mind, and that was to bring the distance between point 1 and point 2 so small, or bring those 2 points so close together that we couldn't tell them apart. Okay? And when we did, we'd get the slope of that secant line. But as this squeezes down to 0, it doesn't become a secant line anymore, because all of a sudden the point might be here, and there's a line, and then the point might be here, and there's a line. Okay, now it's squeezing down to 1 point. In fact, it's going to touch that function at only at 1 point. This is going to be a tangent line now. Tangent means to touch. Okay, so now it's going to approach it as delta x squeezes down to 0. Our secant lines are going to become closer and closer to tangent lines. So we call the limit as delta x tends to 0 of f of x plus delta x minus f of x all over delta x is the slope of the tangent line. Tangent line of our original function. The slope of the tangent line. Okay, now, as we go back though, that was the slope of our tangent line there. So, but what about way up here? Let's say upwards above point 2. What's the slope of the tangent line there? Well, notice that we didn't pick any particular point. And so this is going to give us a general definition of what the slope of the tangent line to f really is. So let's take an example of this. Suppose that we wanted to find the slope of the line tangent to the function f of x is equal to 3 minus 2x. Okay, and we want to find that at any given point. And so let's just choose the point negative 1, 5. All right, so if we wanted to do this, then what we would have to do is find the limit as delta x approaches 0 of f of x plus delta x. And so in place of x, put an x plus delta x in parentheses. So 3 minus 2, x plus delta x, minus, in parentheses goes our function, 3 minus 2x, all divided by delta x. And so as we expand this, we have the limit as delta x tends to 0 of 3 minus 2x minus 2 delta x minus 3 plus 2x all over delta x. Okay, but here we have a 3 and a negative 3. Those cancel. Here we have a negative 2x and a positive 2x. Those cancel. So what we're left with is nothing more than the limit as delta x tends to 0 of negative 2 delta x over delta x. And we learned it under limits that if we can find a function who agrees at all but one point of that, then the value of the function at that point is the value of the limit. All right, so we can divide through by delta x, because even though delta x approaches 0, we never actually say it is 0. And so we are allowed to divide. And so that's just -2. And so what this says is that the slope of the function, the slope of the line tangent to the function f of x equals 3x minus 2x is -2. In this case, if you recall, here is your slope, because this is in the form of y is equal to mx plus b, mx plus b. And so m is our slope, -2. And so the tangent line, there's really no line tangent to it. And so the slope of the line itself is -2. Now, the question is, what is the slope of the line at -1, 5? Oh, it's still just -2. This does not depend on anything else. It's constant. And so the answer to the question is -2. Incidentally, or maybe perhaps not, all of this stuff, that all boils down to the slope of the tangent line. The derivative of a function is a function that defines the behavior of the slope of the tangent line. Okay, and so what we'd really like to do then is we'd really like to find the derivative of something. And so if we call it the derivative, this is denoted. Denoted simply means shown or written as f prime of x. F prime saying by meaning the first derivative. And so we can define then f prime of x equals the limit as delta x approaches 0 of f x plus delta x minus f of x all over delta x. So the derivative of a function is in fact the slope of the tangent line to that function.